Hello mga ka-Johnny! Welcome back to my YouTube channel. Again, this is Sir Raubensun, your partner in learning mathematics. But before you begin in this video, do not forget to click the subscribe button and give me a thumbs up if my video helps you. Okay, in this video, we are going to learn about continuity of a function. And what is continuity of a function? In this video, we are going to identify at what point is our function is continuous, at what point at the same time that our function is not continuous. Okay? So first and foremost, what is where can we say that the function is continuous? First is the function is continuous if it has no gaps. The function is continuous if it has no breaks, and a function is continuous if it has no holes. So again, no gaps, no breaks, and no holes, meaning the function is continuous. Other than that, if the function commits gap, holes, and breaks, meaning the function is not continuous, or we call it discontinuity of the function. Okay, let's try to investigate these two graphs at my back. Let's try to see if this function is continuous or not continuous. Again, when we say that the function is continuous, if it has no breaks, no gaps, and no holes. For figure A, as you can observe, our function is a parabolic function opening upward. Question is, does this function commit a hole? Very obvious, we don't have hole in this part. Second is, does this function commit breaks? Obviously, we don't have breaks in this graph. Third is, does this function commit gaps? Obviously, we don't have gaps in this graph. If you draw this graph, you can draw it continuously without having holes, gaps, and breaks. Therefore, this function is continuous. For figure A, again, our function is continuous simply because we don't have breaks, gaps, and holes. Let's try to investigate figure B. For figure B, obviously, our function is a parabolic function opening downward. Question, is our function continuous? Let's try to investigate. As you can observe, we don't have a small circle at this point. This is what you call a hole. Meaning, once a function commits a hole, therefore, at that point, the function is undefined. Therefore, at this point of this parabolic function opening downward, in this small circle here, the function is undefined. Meaning, the function jumps into this point because the function will become undefined. First question is the function continuous? No. Why? Because we commit either a breaks. We don't have breaks, yes. We don't have gaps, yes, but we have a hole in this graph. Therefore, the function is not continuous or discontinuity at some point. In layman's term, once you draw this graph, you will stop at this point because the function is undefined and you continue in this part. Meaning, that is not continuous at this point. Again, figure A is not continuous or discontinuity at some point because it commits a hole. For figure A, the function or the parabolic function opening upward is continuous because we don't have either holes, breaks, and gaps. In layman's term, once you draw it perfectly continuity or infinitely continuous at in all points of the graph. So these are the definition of continuous and not continuous. Okay, to understand it more, I have another two figures to investigate if what or how the discontinuity or continuous works. I have figure C and figure D. Let's try to investigate figure D. I have this graph, and obviously my graph is a rational function. We believe that a broken line divides these two graphs is what we call asymptote, or an asymptotic function that divides our graph of a function. And obviously, we have this part of the graph and we have another part of the graph, and they are not merged together. Question is the graph continuous or not? Yes, that's correct. Our graph for figure C is not continuous, simply because we commit gaps between our function. Our function cannot continue at this point of our asymptote simply because our function will become undefined. In layman's term, the figure C is not continuous because they are not merged, or they're not connected to each other. In layman's term, again, they are not connected to each other. There is a certain point that our function is separated, and that is through our asymptote. In short, our figure C commit gaps of the function, meaning figure C is not continuous, or discontinuity at some point. Let's try to investigate figure D. For figure D, as you can observe, again, our function is not connected. Therefore, we can conclude that the function is not continuous because the function has breaks at this point, meaning the function is undefined at this point. In layman's term, we committed breaks, or they are not connected, therefore the function is not continuous. Therefore, figure D is not continuous because we committed breaks in our function. They will become undefined at this point. And for figure C, the function is also not continuous because we committed gaps between the functions. In short, these two figures only told us that the function is not continuous or discontinuity at some point. Again, because these two graphs committed gaps and breaks. Therefore, they are not continuous. Okay, let's try to define again continuity and discontinuity of a function through this example. Let's make our example more abstract. Okay, consider the function f of x equal to x squared minus 3x minus 4 all over x plus 1. Okay, we believe that this is a rational function, meaning once your denominator becomes negative 1, therefore your denominator is 0, and if your denominator is 0, that is undefined. In short, this kind of function, or this function, is not continuous at what point? We believe if x is equal to negative 1, our function is not continuous, right? So meaning, we try to avoid that our x will become negative 1 because our function will become undefined, or that is undefined, or we can no longer use that 1. So meaning, since we are trying to avoid one number in our function, therefore our function is not continuous at what point? At negative 1. Again, why we are trying to avoid negative 1? Because as you can observe, that is your denominator. Once your x is negative 1, negative 1 plus 1, that is 0. And your denominator will become 0. And if your denominator becomes a 0, therefore, your function is undefined, and that's a big no-no. We are trying to avoid that point. In short, this function is not continuous at negative 1. Okay, let's try to understand this function. F of x is equal to 2x plus 1. First question is the function continuous or not continuous? Very obvious that our function is a linear function. Once we graph this function, that is a line or a graph, a line in a graph. Question is, are we trying to avoid a certain number to make this function undefined? No. In short, we can able to put any values for x here. We can put 1, 2, 3, 4, 5, negative 2, negative 3, meaning we are not trying to avoid a number to make this undefined. In short, this function is defined in all values of our x. Since this function is defined in all values of our x, therefore, this function is continuous. In layman's term, the graph is connected. It does not commit breaks, holes, or again, the function is continuous. In short, the function is defined in all values of x and it doesn't commit a hole or a break or a gaps. Once you draw that one, you can draw it continuously without jumping. Okay? In short, this function is continuous. Another function that we have to investigate if it is continuous or not continuous. I have here this kind of function. We have function 1, 2, 3, and this following function only works in this following domains on the following value of x. And we believe this kind of function is what we call the piecewise function. Now, f of x is equal to negative 2 whenever your x is less than negative 2. It belongs to negative 3, negative 4, negative 5, all x's less than negative 2. And for the second function, 1, it only works between negative 2 and negative 3 inclusive, meaning negative 2 and 3 belongs to 1. And for 5, it only works whenever your x is greater than 3. That is 4, 5, 6, and so on and so forth. Obviously, piecewise function works at a certain domain. In short, this function works only here, this function works only in this domain, and this function works only in this domain. And we believe in a piecewise function, it doesn't jump into other domains. Meaning 5 does not work in this domain and also in this domain. 2 does not work in this domain and does not work in this domain. And for negative 2, it doesn't work in this domain and it does not work in this domain because they are only working in the respective domains or x's. In short, this kind of function is discontinuity at points or not continuous, simply because we have breaks, we have gaps in between. For negative 2, it stops at negative, closer to negative 2. 1, it only works here, and 5 only works here. So in short, we have breaks, gaps in between functions. In short, this kind of function is not continuous in the following points. Okay, since we happen to identify if the function is continuous or not continuous, here is some points that we have to consider in identifying continuous or not continuous of a function. We can only say that the function is continuous if and only if it follows to all of these considerations. Otherwise, if it violates at least one of these following conditions, therefore, the function is not continuous. Again, if the function follows to all of these conditions, meaning the function is continuous. Otherwise, if it violates at least one of these following rules, therefore, the function is not continuous. So here are the conditions that we have to consider in identifying the continuity of a function at a certain number. First is, f of c exists, meaning once you evaluate the function at a certain number c, or in a given condition, if it exists, therefore, that is condition number 1. For condition number 2, you get the limit of your function as your x approaches to that particular number. If the limit of that function also exists, meaning for condition number 2, your function approved. For condition number 3, once your condition number 2 is equal to condition number 1, that is for condition number 3. In other words, once the function is checked in all of this condition, that is continuous. If not, violates at least one, therefore not continuous. Let's try to get some example on how this condition or this following condition works. This time, let's try to investigate, or let's try to use how those following condition works in identifying that the limit is that the function is continuous or not continuous at certain point. For example number 1, I have here a function 3x squared minus 2, and let's try to identify if the function is continuous at x is equal to 2. How are we going to identify if this is continuous at x is equal to 2? Let's use the 3 conditions that I presented to you. For condition number 1, let's try to identify if f of c exists. Okay? Again, if f of c exists, meaning we are going to evaluate our function at x is equal to 2. Meaning, this is our c. We believe that in evaluation of function, we simply substitute the value of our c at our function. So we believe that our function is f of 2 is equal to 3x squared minus 2. Let's try to identify if it exists. So by simply substituting 2 here, again, where did we get our 2? At the point where we are trying to investigate or evaluate our function. So it will become 3 times 2 squared minus 2. That is 12 minus 2, and that is 10. Question. If f of c exists for condition number 1, yes, f of c exists, and that is 10. There is still a chance that the limit is continuous. For condition number 3, since condition number 1 exists, let's proceed to condition number 2, trying to find if the limit exists at x as your x approaches to positive 2. That is the limitation of f of x as x approaches to c. Again, c here is where your x, where you are trying to identify if your x is continuous at certain point 2. So meaning your x here approaches to 2, and your function is this one. So it will become the limitation of, what is your function? 3x squared minus 2 as x approaches to 2 here. We believe that we've learned a lot of rules in finding the limitation of this one. So the limitation of this one, that is 3 times 2 squared minus 2 using the subtraction rule, the power rule, and the constant multiple rule. So it will become 12 minus 2, that is 10. Question. Is the limit of the function as x approaches to exist? Yes, it exists at the point 10. Since condition number 1 exists, condition number 2 also exists, meaning there's still a chance that the limit is continuous. Let's proceed to condition number 3. What is condition number 3? If f of c is equal to the limitation of f of x as x approaches to c, or in short, if condition number 1 is equal to condition number 2, we believe that condition number 1 exists, and that is 10. So that is 10. And for condition number 2, we believe that the limitation also exists, and that is also 10. And obviously, condition number 1, condition number 2 are equal. Therefore, it is checked or it is approved for condition number 3. Condition number 1 checked. Condition number 2 checked. Condition number 3 checked. Obviously, it follows to all the condition. Therefore, for this function at certain number 2, this is a continuous function at point 2. Because again, it follows to all of the condition. Therefore, the function is continuous. Okay, let's try to identify this another example. We consider this one as our example 2, identifying if it is continuous or not continuous. Our previous example, we concluded that that was a continuous function. Let's try to investigate this one. I have here a rational function, x cubed plus 1 all over x plus 1. Let's try to investigate if the function is continuous at -1 or discontinuous at -1. Let's try to use all the conditions given. First is, you have to identify if the evaluation of function or f of c exists. Again, what is your c here? Your c here is -1 because we are trying to evaluate this one at -1. Again, evaluation. Let's try if it exists. Let's try to substitute that one in our function. Our function here is x cubed plus 1 all over -1 plus 1. F of c, what is your c? That is -1. So now let's continue. In evaluation, we are going to substitute that one. Again, this is condition number 1. It will become -1 cubed plus 1 all over -1 plus 1. So this is -1 cubed, that is -1. -1 plus 1, that is 0. And -1 plus 1, that is also 0. And obviously, condition number 1 is in the form of 0 over 0 or indeterminate form. Meaning, once the function is indeterminate, that is undefined. For condition number 1, is f of c exist? Yes, the f of c does not exist because 0 over 0. Do I have a reason to continue for other conditions? No, because at condition number 1, f of c does not exist. Therefore, there's no reason for you to continue for other condition. If in condition number 1, it does not exist, or it does not follow condition number 1, therefore, there's no reason for you to continue conditions 2 and 3. At condition number 1, you can conclude now that that this function is not continuous at x is equal to 1. Again, why I concluded directly that the limit is not continuous at -1? Simply because it violates condition number 1. As what I have told you, if it violates at least one of the condition of the 3 condition given, therefore, that is not a continuous function. Same thing here. It violates condition number 1. Why did I say it violates condition number 1? Your condition number 1 becomes 0 over 0 and that is undefined. In short, it does not exists. That's how you evaluate functions, if it is continuous or not continuous. Same thing again and again. You follow all the conditions that I presented to you. Okay, so I have now in my last example in this video. Same thing. Let's try to investigate if this function is continuous or not continuous using the three conditions that I presented to you. I will not be tired presenting to you if the conditions follow, therefore that is continuous. If it violates at least one of the following conditions, therefore the function is not continuous. Let's try to investigate this one. H of x, and obviously I have two functions over a specified domain, meaning this kind of function is a piecewise function. Again, this is our function. H of x is equal to x cubed plus 1 all over x minus 1. Obviously, it is a piecewise function over a specified domain. X cubed plus 1 all over x minus 1 only applies whenever your x is not equal to negative 1. Therefore, other numbers aside negative 1. H of x should be 3 when your x is equal to negative 1. Obviously, our function is a piecewise. So our goal again here is to identify if this function is continuous at x is equal to 1. Therefore, let's try to determine at x is equal to 1 if it is continuous or not continuous. Same thing that I did in my previous example. Let's use the following conditions. For condition number 1, let's try to identify if the f of c exists. Meaning, once we evaluate at negative 1, does it exist? Question is, since this is a piecewise function, meaning x is equal to negative 1 only applies to only one function. Does it apply to this function? No, because x is equal to negative 1, the condition is all x except negative 1. In short, x is equal to negative 1 only applies to our function. And our function now here is h of x is equal to 3, a constant function. Since our x here is negative 1, it only applies to 3. Therefore, this is our functions to be used. Let's try to evaluate if the conditions apply, that is continuous. If it violates at least one, that is not continuous. Let's begin to condition number 1. If f of c exists, what is my c? My c here is negative 1. What is my f of x? Or my h of x rather, since my function here is h. What is my h of x? That is 3 because it follows here. This condition only applies to 3, not to the first function. Okay, so that is h of negative 1 is equal to, what is your function? 3. How to evaluate if your function is plainly constant? Since you don't have a need to substitute because we don't have a domain or x here, automatically that is 3. Therefore, h of c exists at what value? At 3. Do we have to multiply at 1? No, because 3 don't have any variable wherein you can substitute negative 1. That is a plainly constant, therefore only 3. Is condition number 1 checked? Yes, that exists at 3. Therefore, there is a reason for you to continue to other conditions. That is condition number 2. For condition number 2, let's try to identify if the limit of h of x as x approaches to c exists. We believe that our h of x is 3 only because it doesn't apply to our x is equal to negative 1. What is your c again? That is negative 1. To become the limitation of what is your h of x? Your h of x is 3. As x approaches to, what is your c? That is negative 1. We believe that we have only constant here. Limitation of 3 as x approaches to negative 1. In short, that is a constant rule. What is the limitation of 3 as x approaches to negative 1? That is 3 applies constant rule. Question now. Is the limitation of x of h of x as x approaches to -1 exist? Yes, it exists to 3. Meaning, condition number 1 checked, condition number 2 checked. Therefore, there is a reason for it to continue to our last condition by comparing the results of the first two conditions. For condition number 3, we have to compare the result. The result here is 3 and the result here is 3. They are 3 is equal to 3. Is 3 is equal to 3? Yes, that is also checked. Question now. Is our function at -1 continuous? Yes, very good. It is continuous simply because condition number 1 checked, condition number 2 checked, and condition number 3 checked. Therefore, this function is continuous at x is equal to 1. Again and again, that's how continuous and not continuous works using the following condition. Do not forget the following. First, identify if f of c exists. Second, if the limitation of the function as x approaches to c exists. And also, if condition number 1 and condition number 2 is equal, therefore, if the following conditions are all checked, therefore, the function is continuous. Otherwise, if it violates at least one of the following conditions, therefore, the function is not continuous. That ends on how we identify if the function is continuous or not. In my next video, let's try to identify the types of discontinuity. Again, this is Sir Raubensun, your partner in learning mathematics. Before you end this video, do not forget to click the subscribe button and give me a thumbs up if my video helps you. See you in my next video. Bye-bye!